I'm going to be talking to you today about a new data portal called NAMERS, which stands for Novel Applied eDNA Metabarcoding References Sequences portal that we built to support applied eDNA metabarcoding. This is work that was done in my lab at Fisheries and Oceans Canada by Kristen Westfall, and we did it in collaboration with Meredad and his group at eDNA Tech, Greg Singer, Munish Kaushal, Scott Gilmore, who's from DFO as well, and Nicole Fonner. So just by means of introduction, I think for a lot of us this is really common knowledge that the need for good reference data for eDNA studies is well known. But I think just as a brief primer, I think it's important that we really understand why. Like, what do we mean by this and why is it so important? So we need taxonomically complete databases. We know that. We know we need them to be trustworthy. And I'm going to argue that we need complete gene representation. And the reason for this is for taxonomically complete, I kind of think of these eDNA metabarcoding studies as like, maybe we have a house and we don't know who's in it. And then we're using another house with everybody in it to determine who's in the house where we don't know who's in it. So with taxonomic completeness, what we're saying is that the house you're using to determine what's in your unknowns, everybody is home, and that's important if you want to be able to detect everyone. In terms of trust, we're saying that everybody is who they say they are. So they're home and they're telling the truth about who they are. And we need that for these results to be actionable. And I'm going to argue we need complete gene representation because not all genes work equally well for all taxa, and we need everybody to be wearing unique outfits so that they're not mistakable for one another. So again, the why, this has to do with ensuring that the methods that we're using to answer our questions are fit for purpose. And so this is in the context of marker selection and thus primer design, and species assignment. So I think we're quite aware that we need good reference data for species assignments. I think we might be a little less aware that we also need them at the front end of study design to ensure that the markers we're using are fit for purpose. So this is what I was speaking to a little bit yesterday about a fitness for purpose context. I wasn't meaning so much that the assays or the methods performance characteristics at the back end in terms of errors and whatnot suits our tolerance limits. I was more thinking that at the beginning, if you actually don't know that your marker even has a reasonable shot at amplifying a target, when it doesn't detect that target, you can't fault the assay. That's actually kind of on you, I think, on the design. Okay, so if we need these databases so much, what are we doing now? Like, how are we living without them? Well, we're using large global data repositories that have variable levels of curation, none of which are ideal for actionable eDNA metabarcoding. As such, we are commonly generating in-house custom libraries, which they seem to work quite well, but they're quite labor intensive to keep regenerating, and they don't follow the fair and care data principles. Okay, so what we did is, we said, okay, let's have a shot at this. Let's see what happens if we build a reference DNA database specifically for eDNA surveys. We just start at the beginning and say, we want to be able to detect freshwater fish in BC, which is true, and I'll show you why. We're looking at a number of species at risk there and trying to learn more about their geographic distributions. So let's use this as a prototype. What happens if we build a database specifically for this applied purpose? The kind of pillars that we used before we started was we said, this is what we need. We need the database to be complete. So what I mean by that, of course, taxonomic completeness, but completeness, it's a metric as well, right? It's like 100% complete means you're done, you're absolutely complete. But a lot of times we're using databases, we don't know how complete they are. So we say, okay, you need to know how complete your database is. Obviously, ideally, it's 100%, but if it's not, know what it is. By complete, we're saying complete gene representation in the mitochondrial genome, because this is the best region usually for doing a lot of eDNA work on vertebrates anyway. And I don't want to get into this, but it can kind of be argued that if you're trying to fill gaps in databases by amplicon sequencing and single marker databases, you're actually also creating new gaps as you fill gaps, because you're contributing to that asymmetrical coverage across genes in the database. Another feature of Complete was we wanted it to have nuclear gene representation, so our database has the nuclear ribosomal genes. Quality was a priority. Everything we sequenced is vouchered in a museum. Virtually everything has a catalog number that you can go back to. And the last is we felt the database needed to be accessible, meaning, just quickly an end user could go and get alignments, could build a custom library. End users who aren't specialists could go surf and tell us how complete the library is, or see for themselves, as opposed to take everything from us like in a big black box and just say, we've got it, when there has been some evidence in the past that we haven't got it. Okay, so I'll show you the database quickly now. It's called Namers. It's at namers.ca. It's still, we're in the very final stages of it. It's live right now, but there's a little beta testing warning that pops up. It's an online mitogenome and ribosomal DNA gene portal. It currently contains about 92% of BC's freshwater fish, all of which were generated from vouchers in museums, or virtually all, and the details are in the paper that is in review. The database is very simple. It has 3 main elements. I'll just show them to you briefly here. There's a data table, and basically along the down you've got all the species, and across you've got all the genes, and end users can just quickly, first of all, see what's in the database, and secondly, click to include and exclude taxa of interest, and then update the table so it takes out things you don't care about. And then you can go to an alignment viewer and pick your gene and pick your taxa and download a FASTA file of just what you're looking for. That's in the alignment viewer. And then there's a species page for every taxon that has the annotated mitochondrial genome map, and you can download the whole genome there, and then it has some links to the FishBase and GBIF pages for that taxon, so you can quickly access some more info. Okay, so just the second part of my talk, I want to just say, okay, so we did that, and then so how useful is it, right? It might look pretty, okay, and users can go mess around, but how useful is it? So we were learning ourselves as we went with this. Obviously, we didn't know as we went. Firstly, what you can do is quite easily take a whole bunch of primers. For us, we were looking at freshwater fish, and take a whole bunch of primers that are used to detect for freshwater fish and throw them at your database and find out in silico how well the primers match your target and how good the species resolution is in that amplicon. So this is very simple to do, and it's something that we're very used to living without, quite frankly. We tend to pull primers that other people used and published on and said they worked well. But this is much more detailed. Incidentally, those species resolution bars, they have that little gray bit at the end because all the lamprey species were not resolved by any marker. So the bars get a little longer when you just exclude those because nothing worked. Okay, this is just another way of kind of using the database when you're at the survey design step is perhaps, we've talked here a lot about general biodiversity, but sometimes in the applied world, end users are very interested in just a specific target group. So here, if you look across families, it's very easy with a database like this to look at the family level of which primers work the best. And on this slide, you can see that it is quite variable across markers and across families in terms of which primers look like they would do the best job. And one of the things, we didn't exactly expect this, but we thought that the database was going to help us with species assignments. We didn't know that we were going to find, just by these 2 plots I've shown you, that we were going to find a marker that we weren't using that looks better than all the other markers we were using. So there's the VERT16S marker, which is in a paper by Vences et al. In 2016. From these 2 analyses, looks better than anything we were using in terms of very low primer mismatch and very high species resolution. Okay, so we went ahead and then applied these in the field. We right now are interested in particular in 5 species at risk freshwater fish in the interior of BC that I have listed here. And when we went out, so before NAMers, this is the level of species resolution we could achieve using 16S and 12S in the field for these species. In general, we knew these species were problematic. It was a driver for generating a new database. But you can see that for the most part, using GenBank, we were able to only get genus level resolution out of these. So what we thought is, and what we put in our grant, this is a Genome BC funded project, what we put in the grant is that we're going to use NAMers to design markers that are more specific to these taxa and can achieve species resolution. What we didn't know or didn't expect is that we didn't even need to do that. The complete database itself did that for us. Now, when we went back and analyzed those same data with NAMers instead of GenBank, my apologies for the dashes. It's because these are real field data, and I should have put in here, well, anyway, these are real field data. So the dashes are just non-detects. It doesn't mean that it can't resolve, it's just we didn't find them. You can see that just by using NAMers itself, we had better species level discrimination. And then a second benefit is we were able to apply this new marker that we discovered by using NAMers, and that did in a way even better because at a single marker we were able to get species level for most things. And then the last column is showing the results of a marker that we designed newly for these taxa, which also performed well. So this slide is just to say we are actively going out into the interior of BC, and we're looking for these 5 particular species of concern. And one of the main question here is what's the real geographic distribution of these, because often limited range excuse me, is used as a criterion for listing. And there's some good reason to think that that's a data deficiency as opposed to a real situation. So we are going out into the field into 3 different river systems and trying to understand what is where, and so when these species are reassessed by COSEWIC, they have more data on their geographic distribution. Okay, so yeah, that's it. There are a lot of people contributed to this. I want to thank, some of them are in the room, thank them for samples, support, linkages, and I just want to put a shout out to eDNA Tech, our collaborators who did a great job of building the portal, and to Genome BC for funding the work. Thank you.